Now, Leung from SOM and myself, Kayleigh Houde from Bureau Happold are going to be talking about the impact of refrigerants. So I'll hand it over to you, Luke, to start. Luke, you might be muted if you're speaking.
Can you hear me?
We can hear you.
Sorry about that. So the goal here, you probably heard Kim Shin talk about earlier, is to work with the architects, structural engineers, and MEP together in harmony to sing from the same songbook, so that ASMEP, embodied, and operational carbon can be addressed together. And one of the major pieces refrigerant that we can bring to the table in terms of the knowledge of it and the impact of it. Now you're looking at the screen here is the whole life cycle of refrigerant, from the production in the factory to transportation to the in-use portion and end of life, and then the recycle. There are these blue alphabets and number in this cycle, and they refer to the EN 15978 standard. Next slide. So we'll touch on two standards here. The first one is EN 15978. Refrigerant actually is part of that A, B, C, D module in EN 15978 or the ISO standards. Next slide. Or go back one. So the important thing to note is refrigerant leakage in this standard belongs to B1, the in-use portion. That's where they categorize the silo of leakage. Now this is in use, but it's part of that whole life carbon, part of that embodied carbon concept. Next slide. Why I say that embodied carbon? Because the way life cycle analysis look at refrigerants, it comes with the building. Next slide. Now this element during the in-use stage, it leak, but that is a way to look at the maintenance that you need to do to the refrigerant that comes with the building. It's almost like your building could have other physical elements that come with it, but will need maintenance. Maybe some of the carpet will need to fix, some of the exterior wall need to fix in its life cycle, but that is not an EUI. Next slide. This is EUI, your actual energy consumption, right? So that whole life carbon framework looking at refrigerant is something comes with the building and needs to be maintained, but not an energy to power the building, not EUI emission. Next slide. But the second way to look at it is scope 1, 2, 3. Now, when we look at scope 1, 2, 3, refrigerant is considered as a fugitive element that emit carbon under scope 1 of direct emission on site. Next slide. But there's a fine difference here because this is the EPA website. It clearly states that scope 1, 2, 3 applies to more for an organization, not life cycle analysis of a building. So I think you will see more people talk about scope 1, 2, 3 in the context of this organization emit that much carbon. And in that context, scope 1 direct emission will include fugitive refrigerant emission. But I think you will hear less people talk about the scope 1, 2, 3 emission of a building. You will probably hear a lot more the whole life cycle of carbon emission of a building. So that's a little fine difference between these two elements. Next slide. When it comes to MEP equipment, as long as the grid is not clean, what you are seeing in a piece of MEP equipment is the bar on the left. Majority of the carbon is going to be in the operational cycle. But if you take away the operational cycle in MEP equipment, especially the one with refrigerant, the refrigerant will be the orange piece. And then the gray is the rest of the physical elements of that equipment. So as the grid get cleaner, the refrigerant will be a significant portion of it. Now, right now, there are already many regulations in certain states that regulate the refrigerant GWP cannot exceed 750. But you may find difficulty even in 750 GWP to look for refrigerant in certain type of heat pumps, for example, is still difficult. But having said that, there are other countries, for example, this building we're doing in Australia, the local engineers already committed to refrigerants GWP of less than 10. So there are ways to get around those. Next slide. One of the key is to actually benchmarking the refrigerant number, maybe starting with this group here. You know, looking at this chart here, you can see when EPA start collecting data, then what they find out is the reclaim of the HFC actually start increasing. So you start getting the data and people start focus on it and then get more recycle of the element. So hopefully we'll start sharing information on the refrigerant, how much refrigerant we need to buy for the building, right? If we're gonna benchmark energy and carbon emission of a building, why not refrigerant? Because they also emit carbon. Next slide. In fact, if you look at the carbon they emit globally, F gases contributes to about 2% of the global emission. So 2% sounds small, but if you think about the annual emission operational of building is about what, 11%? Embodied carbon is 29%. One element of up to potentially 2% is actually quite important. Next slide. Now, F gases compose of a lot of other stuff, but one of the key elements in there is actually refrigerant, which is the kind of the blue line you see on the screen, and it has been increasing throughout the years, becomes a significant portion of the F gases. So we need to start help the architecture, the structural engineers, the ASMEP industry to understand carbon, and this is in our wheelhouse, which Kayleigh will go into more detail. Next slide.
Thanks, Luke, for that introduction to refrigerants. So I'm going to walk us through an example of just how harmful refrigerants are and how impactful they are, just looking at one piece of equipment. So if we look at the data sets that are available around refrigerants presently, we are looking at equipment life expectancy, first of all. So there are a couple of data sets within that. So for GHG protocol and LEED, both reference equipment lifespans. We also have data sets around refrigerant leakage. So the amount of refrigerant that is expected to leak by equipment type, as well as refrigerant environmental metrics. You saw some of those that Luke showed around R410A versus R134A. So there are lots of different data sets that describe those values per kilogram of refrigerant, the amount of CO2 equivalent. So for this example, we will be focusing on a building with a life expectancy of 60 years approximately. We'll see that the area of this building is about 33,000 square feet. If we're looking at one chiller whose cooling capacity is 110 tons, let's say the refrigerant charge for that is 48 kilograms of R410A. The life expectancy for this chiller is about 20 years per GHG protocol. And then the leakage metrics around this, which some of you may not be familiar with, is 1% at installation. About 15% is lost per year. That's for an average chiller per the EPA data set. At end of life, they expect that 5% of that will be lost. And then the amount remaining end of life you expect will be 100%, or that it's fully topped up when it's decommissioned. The environmental metrics around that, if we're looking at R410A, the global warming potential is 2,088 kilograms of CO2 equivalent per kilogram of refrigerant. There's no ozone depletion potential associated with R410A. So if we're looking at just the one chiller that you installed on day one, the amount of leakage that you're looking at throughout its lifetime in those 20 years is 146 kilograms. That's 3 times as much as you initially charged the unit with. That's how much refrigerant you would require for that unit in terms of its loss over its lifetime. That's the amount that's calculated in terms of multiplying by that 2088. So what you're looking at there is then 300,000 kilograms of CO2 equivalent. Now, you might be saying, what does that number mean to me? I don't know what that number is exactly. That's about 35,000 gallons of gasoline, or 55 homes' electricity use for a year. It's an enormous amount of embodied carbon just for the refrigerant of that one unit in a relatively small size building. Now let's multiply that and scale it up to the lifetime of that building. Let's say that you always had the same chiller, same tonnage, same refrigerant type. You're looking at 3 chillers throughout that building's life. Multiply that 146 kilograms by 3. You're looking at about 440 kilograms of loss throughout its life, almost 1 million kilograms of CO2 equivalent, which is over 100,000 gallons of gasoline, 167 homes electricity use for a year, and over 2,000 barrels of oil in terms of its equivalent. You can see that that scales up very quickly just for the refrigerant. Now, if we compare that refrigerant leakage, we can think of these as the actual containers of refrigerant, each of these representing about 25 pounds. That close to 1 million kg CO2, again at 100,000 gallons of gasoline. If we compare that simply to the raw materials required for those 3 chillers that you would install, let's say the steel required for the chillers, those raw materials again, that, according to the Dakin and Train, have both produced EPDs, or some of the very few EPDs available to us in MEP in the US especially. They estimate that A1 to A3, again, that the manufacturers incurred amount of embodied carbon to be 43 kilograms per kilogram. So based on the weight of those chillers or the tonnage of capacity, like about 14,000 kg CO2. So it's almost a factor of 100 times more between the refrigerant itself and then the raw material for the equipment. It's a huge difference, and you can see why we're choosing to focus on the refrigerant piece. If we blow this out to an even wider perspective here, we're looking at a building life expectancy of 60 years again, about 33,000 square feet. If we convert that to meters, it's about a factor of 10, but 3,000 square meters. If we look at the average amount of embodied carbon expected for a building of that size, it's about 600 kg CO2 per square meter. ILFI usually says a value of about 500, but let's round that up a little bit and say they didn't put any energy efficiency measures in. The total building GWP for structures, foundations, and enclosures, so all of that concrete or wood or steel, is about 1.8 million. Let's compare that to the refrigerant number, which came in at almost 1 million. It's 50% of that embodied carbon total, just for the refrigerants. Now, if we take a look at the operational carbon figures, since refrigerant falls somewhere between embodied and operational, you'd expect an energy use intensity of about 42 kilobTUs per square foot per year for a medium office. Let's pretend it's in Seattle. And then the factor for electricity, based on the greenhouse gas factor for electricity from ASHRAE, is about 0.33 kilograms per kilowatt hour. That lifetime operational carbon over those 60 years is expected to be somewhere in the ballpark of 8 million kg CO2. You're still looking at 11% of that would be from the refrigerant of this individual chiller that you'd replace twice. So this stacks up very quickly to a very alarming picture, and we can say immediately, we know we need to focus on this. And we'll go into a little bit more on this. We are building a tool that will be available through the MEP2040 site that I'll talk about in the data analysis and reporting group.